Hello, my name is Liu Yuxin, and my student ID is 1130-15040. And today I'll be talking about task 1, from question A to question F. And first, in question A, I will solve this equation by using the force equilibrium, which is the force balance. And because in the picture, the electron is traveling in a circular orbit around the nucleus, and electron is carrying a negative charge. The nucleus, however, is carrying a positive charge. So what happens now is that there will be a force, a Coulomb force between them two, a attraction force, and it actually provides the centripetal force so that the electron can continue to travel around the orbit. So by applying the force balance, we can obtain the radius r. First, the centripetal force equals mu v squared over r, and the Coulomb force equals 1 over 4 pi epsilon naught times z squared over r squared. And these two forces equal each other. Centripetal equals F Coulomb, so we can get that by solving the equation. The radius r equals z squared over 4 pi epsilon naught times mu v squared. And this is question A. And now let's dive into question B. And first, we assume the electron as a matter wave, 物质波. And by the Bernoulli relation, lambda equals h over p. And the p here is actually the electron's momentum. E equals mu v. So we get that the wavelength lambda equals h over mu v. And the second thing we do is, because circular orbit must satisfy standing wave condition, 驻波条件, in Chinese for reference. So as in the picture right here, 2 pi r is the orbit the electron travels, and its length is 2 pi r. So 2 pi r equals n times lambda. And n here is a positive integer, 1, 2, 3, and so on. And now we substitute lambda we derived earlier. Lambda equals h over mu v. We can get that the radius r is n times h over 2 pi times mu v. And to make the equation look more beautiful, we substitute h bar equals h over 2 pi. So now we get that r equals nh bar over mu v. This is the answer of question B. But let's do a further discussion right here. So if we look closer, we multiply mu v at both sides of the equation. You get that mu vr equals nh bar. And mu vr is actually the angular momentum of electron. And n is a positive integer. This actually means that the angular momentum is quantized. So only certain circular orbits are allowed for the electron to travel. And this is question B. And in question C, we want to derive the energy equation of the electron. And my approach is we first calculate the potential energy of the electron. So we know the Coulomb force is 1 over 4 pi epsilon naught times z squared over r squared. So since energy is actually a force times a distance, so potential energy equals minus the Coulomb force times the radius r. So it equals minus z squared over 4 pi epsilon naught times r. And later, we use the virial theorem stated by the question. The kinetic energy equals minus 1 over 2 times the potential energy. So the total energy now becomes the sum of kinetic energy and the potential energy. So it is 1 over 2 times the potential energy. So now E equals minus z squared over 8 pi times epsilon naught times r. And now we use the standing wave condition, angular momentum. By part B, we know that mu vr equals nh bar. And we can know the velocity v equals nh bar over mu r. And by question A, earlier, we know the radius of the electron is z squared over 4 pi epsilon naught times mu v squared. So by substituting v with equation 1, we get that the radius is z squared over 4 pi epsilon naught mu times nh bar over mu r squared. And by calculating this, in the end, we get that the radius r is 4 pi epsilon naught times n squared h bar squared over mu z e squared. And since we know the radius, we can actually substitute it back into the energy formula. So now the energy formula becomes this. If we substitute it into here, the R becomes mu z e squared over 4 pi epsilon naught n squared h bar squared. And now we know that the energy is minus mu z squared e to the power 4 over 32 times pi squared epsilon squared and h bar squared times 1 over n squared. And now we let ry star to be a constant to be a nature constant. So we assume ry star is mu e to the power 4 over 2 times 4 pi epsilon naught squared h bar squared to make the equation look better. And we substitute it into the energy formula. We get that En is minus ry star times z squared over n squared, which is the answer of question C. And before that, we can conclude a few things. The first thing is that energy is actually quantizable. Because n is a positive integer, it can only be 1, 2, 3, and so on. So energy is quantized. And the next point is that energy is negative for the electron, of course. So En is always smaller than 0 in the equation. This actually indicates that the electron is always in a bound state. And the third part is that the larger the n means the higher the energy is. So for reference, n equals 1 is the lowest energy. It is the most stable state. And n equals 2 and 3 and so on, it means that the energy is higher. But however, energy is always smaller than 0. So the higher the energy is means that the energy is closer to 0, the less negative it is. So the fourth part is that we observe that energy is actually scale with z squared. And this means that the bigger the nuclear charge is, the stronger the bound is, and the lower the energy is. So these are our discovery of question C. And now let's dive into question D. And by question B, we just derived the angular momentum of the electron, L equals mu RV and equals NH bar. And now, we will make a discussion on the possible consideration of quantized angular momentum. So the first thing is we compare classical mechanics versus the quantum world. As you can see in the picture, in the classical world, the angular momentum is continuous. But on the other hand, in the quantum world, the angular momentum is discrete. So in the equation, L equals mu RV. This means that L can actually be any value, any possible value. But in the quantum world, L equals NH bar. So L can only be discrete value. As you can see, just like the steps, N is a positive integer. So is L. And the second discussion is we will explain why quantum size happen. This is actually because of the wave condition 驻波条件 in Chinese for reference. Since 2 pi r equals n times lambda, so mu vr is NH bar by part B. Just like the picture. And the third discussion is we want to do a small discussion about Bohr and de Broglie, the Broglie. These scientists contribute a lot in the discovery of the matter wave. And Bohr assumes that L equals NH bar. And de Broglie actually makes a further discussion about that. He derived a much deeper understanding from the wave nature of the matter wave. Lambda equals h over p, and p is the angular momentum. E equals mu v over here. And the fourth discussion is the physical meaning. The physical meaning of L equals mu RV is actually that only certain orbits exist. So in question E and question F, we will make a discussion of our observation. As you can see in the picture, the lines are actually discrete. The spectrum is composed of discrete spectral lines, not continuous spectrum. And each line corresponds to a specific frequency. The atom emits only certain allowed photon energies, 只释放特定的光子能量 in Chinese for reference. And the question states that it is the hydrogen atom's Balmer series. And the Balmer series means that it is transitions from higher level down to n equals 2. So when energy level is 3 or 4 or 5 or higher, when it transitions to n equals 2, all of that photons, all of that energies, they make up the Balmer series. So for reference, you can look at the energy diagram over here. It describes that when n equals 2, it's right here. And the red line is the photon. The photon is in the transitions, and it will emit photons, photon energies. And n is only a positive integer, so we can know that the wavelength 1 over lambda is equal to RH times 1 over 2 squared minus 1 over n squared. And this is the frequency of the electron, of the photons. So when an electron transitions from a higher energy level N down to a lower level M, the energy difference delta E is En minus En. The energy is emitted as a photon with frequency V. Delta E now is h times V and equals to hc over lambda. And c here is the speed of light, which is 3 times 10 to the power 8. And we substitute lambda from equation 3. We can get that delta E, the energy difference, is actually equal to minus Ry star times z squared times 1 over n squared minus 1 over 2 squared. And this is the Balmer formula we just derived. So the energy equation we just derived in question C can be used to derive the Balmer formula. And as you can see, the lines are closer at higher frequency because En is directly proportional to minus 1 over n squared. The spacing between adjacent energy levels decreases as n increases. So approaching series limit at n is infinite, since En is minus Ry star times z squared over n squared. This is the result in C. So this is our discussion for task 1.